Hello everyone, myself Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So, in the previous session, we have seen the problems on shear flow in open section beams by considering the formula for shear flow of open section beams, and then we deduced how to calculate the shear flow distribution, okay, for panel 1, 2 and 2C and everything. Now, in this session, we are going to see additional problem on shear flow of open section beams. And in the previous previous session we considered unsymmetrical problem. Now in this session we are going to consider one symmetrical problem, and we'll see how that equations will reduce and how to calculate the shear center for the open section beams also we are going to see here. So the learning outcomes in this module, students are able to analyze shear of open section beams, and students are able to determine the shear flow distribution in the open section beams. So let's try to consider a question which is on channel section, which is given over here, and he is asking to calculate the position of shear center of the thin walled channel section shown in figure, and he mentioned that thickness T of the walls is constant. Okay, so shear center. Now here we have seen in the previous sessions we defined shear center. So shear center is nothing but the point in the cross section about which there exists no twisting moment. And since it is a point in the cross section of any of the element what we considered, so it will have two positions just like centroid. It will have one horizontal position of shear center and it will have one vertical position of shear center. That is, you can assume it as SS, XS and YS. Okay. So now to calculate the position or to calculate the shear center position, we should know two positions. One is the horizontal position of shear center and one is a vertical position of shear center. And to calculate the horizontal position of shear center, we should have a vertical load. Okay. And if you don't have vertical load, you need to assume a vertical load. If you want to calculate the vertical position of shear center, you should have a horizontal shear load. Again, if you don't have a horizontal shear load that is given in the beam section, then you have to assume a horizontal shear load Sx. Okay. So two positions you need to calculate. One is the horizontal position of shear center Xs. One is the vertical position of the shear center, that is Ys. Then only you can say that the shear center position. Okay. But for the problems with the axis of symmetry, and this position of calculation of the shear center reduces. Okay. So how it reduces? For example, you consider this. So you consider the channel section. So the channel section is having horizontal axis of symmetry. Okay. So for the problems which have horizontal axis of symmetry, we should calculate only horizontal position of shear center. Okay. Vertical position of shear center is not required, because vertical position of shear center from the axis above or below, it is the same distance. Okay. In other words, the position of shear center lies on the axis of symmetry. So since this problem is having horizontal axis of symmetry, the shear center lies on this axis of symmetry, but we don't know whether it may lie here or here or here or here, anywhere. So it may lie anywhere on the axis of symmetry, so that we need to find out its horizontal position of shear center, where it lies, at what distance it lies on the horizontal axis. So that is what important here. Vertical position of shear center, straight away we can read out from the diagram itself. Okay. So for this problem, since he asked to calculate the shear center, and we need to calculate only the horizontal position of shear center only, because axis of symmetry. And for that, let us assume that the shear center lies on axis of symmetry somewhere here. And as we discussed, to find out the horizontal position of shear center, we should assume a vertical load Sy. So through the shear center position, and we are assuming one vertical shear load, that is Sy. Okay. Let this Sy vertical shear load is acting at a distance of zeta s from the web 2-3. Okay. So we are assuming that shear center may act here, which is at a distance of zeta s from web 2-3, and at shear center there exists a vertical shear load which we are assuming, that is Sy. So the position of shear center is XS, YS, Okay, so this is channel section he has given, and we know that it has got two flanges, 1, 2 and 3, 4, and one web, that is 2, 3, and the centroid. And for this section, the very first thing is nothing but what? Determination of centroid. So from the inspection, the centroid of this channel section lies over here, and that is the important one. Okay, so this is how we calculate the shear center position. Okay, but to calculate the shear center position, before that we need to calculate the shear flow distribution. Then only it is possible for us to calculate the position of shear center. Without shear flow distribution, you cannot be able to calculate the position of shear center. That you have to understand. Okay, so whether if the question is asked to calculate the shear flow distribution, we straight away take the formula and we calculate the moments of inertia, we substitute, and we take it for the flanges and the web separately, and then the shear flow distribution is over. But if the question is asked to calculate the shear center position, so we have to do all the procedure of shear flow distribution first, and after completing the shear flow distribution, then you have to take moment about suitable point and equate that to 0 by using the equilibrium condition, and then you are going to get the shear center position. Okay, so to find out the shear center, first we need to go with the shear flow of distribution regular procedure. So first let's look into this problem, the shear flow distribution. Also, the formula, if you try to look at the formula, QS is equals to minus of Sx Ixx minus Sy Ixy divided by Ixx Iyy minus I square xy integral 0 to s t into x into ds minus Sy Iyy minus Sx Ixy divided by Ixx Iyy minus I square xy integral 0 to s t y ds. So this is the formula for shear flow distribution for open section beams. Now out of this formula, and our diagram which is given, channel section is having axis of symmetry, that is you can substitute for axis of symmetry Ixy equal to 0, and to calculate the vertical position of shear center, to calculate the horizontal position of shear center, we are assuming a vertical load Sy, so that Sy can be considered as Sy, we are assuming, and Sx is not required, so that you can consider it as 0. Okay, so in the analysis you can consider Sx also equal to 0 because it is not required. Okay, so by these two, substitution of Sx equal to 0 and Ixy equal to 0 into this formula, so here this numerator completely goes to 0, Ixy, so that this entire thing goes to 0, so this term completely becomes 0, and in this, the second term 0, this one term 0, and you left with only this term. In this also Iyy gets cancelled, and you left with only minus Sy by Ixx integral 0 to s t y ds. So for the problems, if it is having one axis of symmetry with Sx equal to 0, our formula reduces to Qs equals to minus Sy by Ixx integral 0 to y ty into ds. Okay, and now this you have to take it as equation 1. Okay, equation 1. Now after this, it's very important for us that to proceed in the formula problem, and you need to calculate moment of inertia for it. Okay, moment of inertia. So now when it comes to moment of inertia in the problem, again after substituting Ixy equal to Sx equal to 0, the formula is reduced, and in this formula you don't find Iyy, you don't find Ixy also here. So you only have Ixx, so just it is that sufficient to calculate Ixx only, not required to calculate Iyy and Ixy for this problem. Okay, and when you try to establish a relationship for this channel section to calculate the moment of inertia, Ixx, let's look into this problem. Yeah, Ixx. So to calculate this Ixx, what you can do here, it is you can do it for 1, 2 and 2 this C dash you can consider, 1, 2 and 2C you can consider Ixx, and rest of the things you can multiply by 2 because of symmetry. Okay, so Ixx equals to Ixx for 1, 2 plus Ixx for 2 C dash, and that will be multiplied by 2. Okay, and for the first one, Ixx BD cube by 12, B is B only, depth is nothing but you can consider thickness, that is T cube by 12 plus area is B into T into y bar square. The center of this one is here, center of the total figure here. This is the distance y bar, that is h by 2. So that is minus h by 2. Basically it is below x axis. So minus h by 2 whole square. That is for the first one, plus second one for 2 to c. So 2 to c, again b is nothing but width thickness t, that is given here. So b into d cube, depth is nothing but h by 2. So h by 2 whole cube by 12 plus area t into h by 2 is the area, and its y bar square. So its y bar square is nothing but for this problem for 2c. So the center of the figure 2c is here and total figure centered is here. So this is the distance what you consider. Okay. So that is h by 2 by 2, that is h by 4. So h by 4, usually it is minus, so minus h by 4 whole square, and completely it should be multiplied by 2, that you should not forget. And now again in this, the first term bt cube by 12, from the thin wall approximation you can make it to 0, and rest of that things you can calculate. So 2 into, and this you are going to get bt h square by 4 plus, and this one you are going to get th cube by 8 into 12, that is 96, plus this one th cube by 16 into 2, 32. Okay, and again if you try to multiply this 2 inside, you are going to get bt h square by 2 plus th cube by 48 plus th cube by 16, that you are going to get like this one. Okay, further you can reduce this equation to get what is written here, that is this one, h cube t by 12 into 1 plus 6b by h. So you can reduce that form of the equation here. So completely you can take th cube by 12, you can take common, and when you take this common and you left with here b by 6b by h plus 1 you are going to get here. Okay, yeah, so this is what you are going to get here, h cube t by 12 into 1 plus 6b by h. Okay, so that is what ixx. So once you get this ixx, you have to take and substitute here, that is one thing. So next thing is nothing but, once you get this distribution, you have to go on for finding shear flow for 1, 2 and 2c. Okay, that is important now. So when you try to substitute ixx, whatever you get here, you are going to get qs equals to minus 12 sy by h cube into 1 plus 6b by h integral 0 to s y ds. You can consider this as equation 2. Now for the flange 1, 2 you have to go. Okay, once you get this distribution. So this is a shear flow distribution. Okay, next we are going for flange 1, 2. So for the bottom flange 1, 2, and what you have to substitute here is you only have y in the distribution. So there is no requirement of x substitution also. Just you need to substitute what is y from the diagram. So for that, what you are doing here, you are considering the distribution from 1 S1 as the distribution, so that you need to get y. But S1 is a horizontal distribution, so it is nothing to do with y. So y is the same distance from the centroid to the distribution from here to here. So it is the same distance h by 2, but it is, since it is below x axis, you have to substitute it as minus h by 2. So y equals to minus h by 2, you have to substitute in this equation. And if you try to substitute in that equation, then you are going to get y equals to minus h by 2, and you left with h by 2 is anyway constant, and minus into minus, you can, this already there is a minus, and minus into minus it becomes plus, and h by 2 when you do, you are going to get 6 sy by h square 1 plus 6b by h, and integral 0 to s ds is there, that will become s1. Okay, so this is again the distribution. What is this? 1, 2 distribution. Okay, now after that you have to apply the boundary conditions. So what are the boundary conditions? So the first boundary condition is at 1, s1 is 0. Substitute in equation 3, you are going to get q1. So when you substitute in s1 equal to 0 here, you are going to get q1 equal to 0. So you remember that always for the open section beams, always when the section is open, at that point the shear flow is always 0, Q1. Either here also Q4 is 0. Wherever the section is open, at the open section the shear flow is 0. Okay. Now next, if you want to calculate at 2, the distance of S1 it covers is B. So you have to substitute S1 equal to B, and it becomes Q2, that is equals to, in place of S1 you substitute B, so that you are going to get 6 SYB divided by H square into 1 plus 6B by H. There is no change in that. So this is Q2. Okay. Right. So from the bottom flange 1 to 2, we calculated shear flow, that is 1 to 0, and Q2 also we calculated, that is equals to 6 SYB then divided by H square into 1 plus 6B by H. So that is how we calculate the distribution. Now since what we want, the question he asked is nothing but to calculate the shear center. So once you get the distribution, now we are moving on to calculating the shear center. 2C is also not required, because 2C dash is also not required. We are not calculating any C dash shear flow here. Our aim is not to calculate shear flow distributions, but whatever the required shear flow distribution, that if you calculate, it's sufficient, because to calculate the shear flow center, Okay. So now how do you get shear center? As we discussed here in the starting of this one, to get the shear center position, we have to take the moment about a suitable point and equate that to 0. So now for this problem, what we are considering here, we are considering the moment, equating the clockwise moments of the internal shears about the midpoint of the web to the clockwise moment of the applied shear load about the same point. That gives, what is that? We are trying to equate the clockwise moments of the internal shears about the midpoint of the web. Where is that web? So we considered here shears channel section. So this is the midpoint of the web. Okay, which we assume it as C dash. So here we got distribution, shear flow distribution. Here we got, this is 1, this is 2, shear flow distribution we got, and now we are considering the distribution straight away, and then we got shear center here, which is SY, and the distance here is zeta S. So when you try to calculate moment about the shear center, first we are writing moment due to shear SY. So the moment due to SY is the vertical shear load, and zeta S is the perpendicular distance. So on the left side we write SY into zeta S is the moment, and that should be equated to the moment due to shear flows. Okay, so shear flow, that is 1 to shear flow, here we got the distribution. Okay, and how we have to write that? Okay, and the distance from here to here, it is B. Okay, so that we have to write it as, so this shear flow anyway we not calculated, and it is passing through the same point where we are calculating moment, these two shear flows. So okay, so this shear flow passing through C dash, this shear flow is also passing through to C dash. So this doesn't give any perpendicular distance to calculate the moment, so no need to consider these shear flows, because the perpendicular distance is 0. So if the perpendicular distance is 0, even the moment is also 0, so no need to calculate that. But the other two shear flows, that is 1 to 2 and 3 to 4, will give moment. 1 to 2 shear flow and 3 to 4 shear flow will give moment. Will give moment about which point? Will give moment about C dash. This is C dash. Okay, so they give moment about C dash. So that what we are doing here, it is we are writing it as 2. Okay, we are multiplying by 2 and writing for only 1 2, because it is symmetrical, right? So Q1 to what you get, it is similar like Q3 4. Okay, so for 1 2, what I am writing here, the shear flow integral 0 to B, limits integral 0 to B, shear flow is Q1 2 is a shear flow, and since we need to write the moment, so the shear flow, that is Q12, must be multiplied with the length on which it is acting to convert into shear force. So what is the length? So this is the distance, what we are Q12, that is nothing but B into perpendicular distance from here to here is nothing but what? H by 2 into ds1. Okay, so this is how we have to write. Okay, even b is also not required here because we taken the distribution integral 0 to b. So straight away you can write q12 into perpendicular distance h by 2 into ds1 you can write. Okay, so q12 into h by 2 into ds1 is the perpendicular distance, is the moment. So q12 is the shear flow, multiplying with since ds1 length is there, it becomes the shear force, and h by 2 is the perpendicular distance, so now it becomes the moment, bending moment. Okay, so now we got the q12 distribution, and take the distribution and substitute over here. Okay, so what is the distribution? Yeah, q12 distribution is this one. What is this? q12 equals to 6 sy by h square 1 plus 6b by h into s1. So take this and substitute over here. Okay, then it becomes in place of q12 we substituted 6 sy by h square into 1 plus 6b by h into h by 2 into s1 into ds1. So here 1 h will get cancelled here, and you're going to get 2 3 just 6, and then it becomes, the equation becomes what? So 2 integral 0 to b, and what is left here in the numerator? 3 sy into s1 sy into zeta is equals to divided by h into 1 plus 6b by h. This is only left, out of which sy and sy gets cancelled. Remember, to calculate the horizontal position of shear center, we assumed vertical load sy. Now that vertical load will get cancelled on itself by when you take the moment about the suitable point. That is the moment due to the shear load is should be equals to moment due to internal shear flow. Okay, it will get cancelled. Now rest of the things is only what we do is the integration. So 2 into 3 it becomes 6, and s1 and rest of all the thing you can write similar, 1 plus h into 1 plus 6b by h. Okay, and here it is s1 you have. So s1 integration you get s1 square by 2, but here you have to substitute the limits as 0 to b. Okay, this further you are going to get 3 divided by h into 1 plus 6b by h into s1 square, that is b square you are going to get. Okay, so finally you are going to get 3b square divided by h into 1 plus 6b by h, which is nothing but the shear center position theta s, which is nothing but this one. So this is how you calculate the shear center position for open section beams. So let's go back and see once what we have done here for this problem. So first the problem is given here to calculate the shear center position, and to calculate the shear center, first we have to calculate the shear flow distribution, and since this is symmetrical about horizontal axis, we have to calculate only horizontal position of shear center. And to calculate the horizontal position of shear center, we have assumed vertical load such that it is acting through the shear center of the cross section, and we assume that zeta s is the distance of shear center from web 23 to the shear load. Okay, and then we return the formula for the shear flow distribution, in which we assumed sx since because of symmetry ixy is 0 and sx also 0 horizontal shear load. When you substitute, the formula reduces to this equation, and calculate ixx, that is you got this one, substitute here and you are going to get this equation. Once you get this equation, first consider the bottom flange, and then you get the shear flow distribution for 1 2 like this one. Once you get the shear flow distribution, and then you have to calculate the shear center by considering the moment, that is moment due to shear load must be equal to the moment due to internal shear flow. Okay, so this is the moment due to shear flow, shear force, and this is the moment due to shear flow, and when you take the moment and substitute, you are going to get the horizontal position of shear center. Okay, so that's how we calculate the shear center positions. And even if the section is not symmetrical, then you have to find out both position of shear center xs and ys. Okay, if the given figure is symmetrical about horizontal axis, you need to calculate only horizontal position of shear center. If the given problem is about vertical axis of symmetry, then you have to consider only vertical shear center. That's sufficient. Okay. So thank you for watching this session, and in the next session we are going to see the shear flow in closed section beams and probably calculation of shear center. So thank you everyone.